Well, thank you very much for letting me speak. It's a great honor. Thank you, Chris, for inviting me. Thank you, Marek, for the introduction and for letting me talk about your work. So let me just go straight into the topic. First, I'll talk a little bit about the motivation, why we're working on this, and Marek already covered some of this. Then I'll summarize a little bit a few aspects of this Planck-Kleinert crystal. And then I'll ask the question, why really quaternions? Doesn't it make it harder than simpler? Why would we do that? Then I'll summarize Marek's work from the last paper, basically. So I won't go into all the details because you can see it in the video from 2021 and the papers. Because then I'll also want to cover a new topic about spin 1/2 visualization, basically. So now, as you know, there's so many interpretations of quantum mechanics. It's pretty crazy. Doesn't that make you wonder why we have so many interpretations? I mean, if you think about this, right, there's people who think, the world splits every time there's a measurement, other things, there's a pilot wave, but also on top of it, there's also a particle. Then we have the idea that, the Copenhagen, where the wave function collapses instantaneously. Why do we have so many different interpretations? It makes me wonder, maybe is it because we don't actually understand quantum physics, right? And that's also what Marek was saying. Nobody seems to really understand it. And so at least that's what's driving me is I want to understand not just the mathematics, but I want to understand how the world works in detail, the actual mechanics. I'd like to understand, derive it from first principles. So, and that's why we are talking about this interpretation down here. Sometimes I've heard a word called wave monism. It's actually originally proposed by de Broglie. And in this interpretation, it's very, back to the basics, really, from the ground up. The idea here is the wave function is real. There is a medium, and there are no particles. Everything is just the wave function, basically. Now for us, it's normal these days to talk about all these interpretations, but imagine if we talked like this about ships. I just had a discussion on the forum the other day about this, so that's why I thought I would bring it up. Imagine we didn't know how ships work. Let's say we just had the formula and we didn't know why they're floating, and we had all these interpretations, right? So the many worlds would say, every time you put a ship in the water, the universe splits in one, it floats, in the other it sinks. Or maybe, the Copenhagen, where there's this mysterious force, and only when you enter the ship it's decided if it will float or sink, and before it's both floating and sinking. Now, this is kind of funny because here it's obvious that it makes sense to try to understand how it works, because, imagine if we didn't know how ships work. How could we build new ships? How could we do research if we didn't actually understand the mechanics? By the way, this picture is from AI generated, and I love AI, so I had to bring one picture in from AI. So maybe it's not such a bad idea to really go back to these assumptions that were made a long time ago and maybe question some of them and revisit some of these models that were abandoned. So, and there are some smart people like Schrödinger. I heard he wasn't a very nice guy, but he was definitely very smart. He always thought the waves were real. And he was very much opposed to this probability interpretation, even though everyone loved it, but he was very doubtful. And also Einstein, who I hope you agree is pretty smart, he actually thought that space must be real and rigid. He said clearly that the special theory of relativity does not compel us to deny ether. He said, according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. And he even said space without an ether is unthinkable. So is it really so crazy to go back to this and take a look if maybe it makes sense after all? And I won't have time to go into all the details, but there's so many experiments these days, so many things that really support the idea. This is just one example out of many. Maybe you've heard of phonons with N, phonons, plasmons, polaritons. These are all quasi-particles. So they are actually vibrational modes. And they behave just like photons. They're even quantum-mechanically described just like photons. But here we know there's nothing weird about it because it's just vibrations actually, in crystals, for instance, or other materials. And you can even do these double slit experiments. You can, all these things you can do with photons, you can do with phonons, but there's nothing weird. So why should it be so different for photons? Here, there's clearly medium. All these waves can be generated with this medium. So why not for photons? Now, Marek has already talked about the Planck-Kleinert crystal a little bit. So basically, what Hagen-Kleinert showed is he proved that the Planck-Kleinert crystal is equivalent to Minkowski spacetime. So here we have 3 spatial dimensions, just normal space, and of course time, but time is in this case not mixed in. But then we have density, right? And I think, was it Manfred asked something about this? So basically imagine this crystal doesn't have the same density everywhere. So where there's a lot of matter, and of course in this case matter is actually waves. So where there are a lot of waves, the medium is denser. And this basically means we have an optical mechanical analogy of general relativity, basically refraction, just like how your glasses work. So, and this is not just an analogy, because, and I'm going to show you an example right after, people working in optics, they use the equations, they use the general relativity metric tensor to calculate these things. So it's more than just an analogy. Of course, this elastic solid has to be deformable by longitudinal and transverse waves. And so why does it have to be solid? Well, because it has to support transverse waves. You can't really have transverse waves in a liquid, or I'm not sure how you would do that. And in this model, everything is waves. So it's not the same as the pilot wave thing, right? In the pilot wave, you have waves and particles, and here you only have the waves. Here is just one concrete example of optics. So here these are actually optical black holes. And so on the left side here, you can see the experiment. This is a medium, an optical medium that gets denser as you go into the center. And when they shine a laser towards this optical medium that gets denser, the light waves are bending towards the center, as you can see. This is just refraction, right? There's nothing weird about it, but it behaves the same way as a black hole, and they use the same equations. So maybe it's not so strange to think about this in this analogy. So what could this crystal look like? And of course, we don't know, right? We really don't know. Nobody can see it. This is just something I found. This is from Marek. An example of how this might wobble, this crystal. So how do we now get from this idea to quantum mechanics? And as Marek already mentioned, and he has worked on this for many, many years, and he has many papers on this, it starts with Cauchy, right? So imagine you have this elastic solid here, and you have this displacement field. So because things can be compressed, and you can have torsion. So basically translation and rotation. And there are certain conditions. So for instance, closed curves stay closed, so you can't break it apart, right? The universe doesn't break apart. And there's the it's basically continuous deformation. And these are some conditions that are the basis for the equation of motion. That's the next one. And Marek also mentioned this one. So here's a simple simulation. This is actually a spin 1/2 wave, but later I hope you will see why it looks that way. So the equation of motion, what does that mean? So the U here is the actual, so if you look at these green little blocks here as just grid points, this is not what the crystal looks like. It's just grid points, right? And basically the acceleration of these elements here is equal to the gradient of compression and the twist of the twist. That's the Cauchy equation of motion. So, well, what do we do now, right? How do we get from this to wave equations and to Schrödinger? Now, again, I'm not going to go through all the details because I talked about this last time. So just the summary, basically, the starting point is Cauchy plus Helmholtz. And I'm sure most of you know the Helmholtz decomposition. It's quite simple, really. So when you have a vector field, you can basically split it apart into a irrotational compression part and a rotational twist part. And I know it's obvious, but I like to have videos. Makes it more interesting, I hope. So obviously this is the compression part here, and this is the twist part. So you can any vector field you can split into these two parts. And so now, well, what do we do now, right? Now we have to do all the math. Now, as Marek said, it's really hard to do the math with vectors. They're just not very nice. There's no division, and so that's, again, maybe we should try something else. So maybe quaternions might be useful. And you'll probably all know what quaternions are, but I want to show a more practical side about quaternions, because quaternions are really used in computer graphics. And I do, I like to do computer graphics and stuff like that. So I use quaternions all the time. They're used in robotics for what? They're used to describe basically twist or rotation. So a quaternion is really nothing else, but you have the three coordinate axis, X, Y, and Z, and that yellow arrow here is basically one quaternion describes a rotation, the axis of rotation and the particular angle, and that's what the quaternion really is. It actually corresponds to bivectors and also to Pauli matrices, and I'll talk a lot more about these later. Just as an example, so like if you're used to using Euler angles and you want to rotate something around an axis with Euler angles, then this is how you would translate it to the quaternion. Like if you want to program it, right, then you would program it that way, basically. And now I know you know all these rules, right? I times j is equal k. And when you view this as a rotation and geometry, it's really trivial. I mean, if you think about this, right? If let's say if I is a rotation in this direction and j is in this direction, and then obviously k is in this direction, then I and then j is the same as if I had done k. It's really, any 7-year-old would understand, right? It's very, and I like this. I like it when things are kind of obvious, when you really understand something, it should be obvious. Some other motivation, and I love the Tesla robot, so I had to add a picture of that one. Quaternions are used in kinematics when you have to calculate, for instance, the joint movement of anything, whether it's a hand or anything with foot. You have multiple rotations, multiple quaternions. Imagine you're moving a joint or a hand from here to there, then you have a number of rotations in between, and that gets kind of tricky if you use Euler angles. So it's much easier if you have quaternions, because it's very clean. Because you can just multiply the quaternions. You can have one times the other times the next times it's very easy. You don't get any weird things like with the Euler angles. And of course, in movies and game development, any game developer knows quaternions, because you have to move cameras around. This is really, actually, for software engineers, this is kind of easy. There's also actually more practical examples, like for Apollo 11. They actually had this problem with the gimbal lock. So this is when the axis, they align, and they even had a special button with a warning line like that the gimbal lock happened, and they had to manually start to navigate because the system didn't work anymore. So you don't get these problems with quaternions. So let's get back to the problem there. So I hope I have convinced you quaternions are actually nice. So how about, instead of vectors, let's just use quaternions then, right? Because you can easily represent the twist, you can multiply and all that stuff. Very nice. So that's what we're doing. And so now all we have to do is combine Cauchy plus Helmholtz. So we just apply the Helmholtz to the Cauchy equation. And again, I won't show all the steps because you can see this from the 2021 video and in the papers. So when you do this, it's very easy, really. You immediately get the longitudinal waves when you do that. So you have one type of wave, and then when you apply it to the other side, then you get, obviously, you get transverse waves, right? This is pretty obvious. And then, of course, you can, of course, combine these, obviously. And that's why, get many shapes of waves, like Marek has actually shown in his talk. So let's continue that. Now, what else do we need to do? Now, we want to actually get to Schrödinger, right? Now we just have wave shapes. So what do? Well, the thing is, we have to bring in energy somehow, because, yeah, we need to, include energy. So let me just play this here. So we have to think about what it means, energy in a deformation field. So let's just look at a certain volume of space, omega. Let's say this space here we are seeing right here. And of course, I've only shown 2 planes because if I show all the grid points, it gets really messy with the simulation. So I'm just showing some wave here. So what kind of energy do we have here, right? I mean, it's actually pretty obvious too. And I have highlighted just one grid point, this red one here, and you can see how it's moving back and forth like a pendulum. Right, you can see that. So what kind of energy do we have? Well, we have kinetic energy, obviously, right? These grid points, these elements, they move at a certain velocity. So that's one part of the energy. Then we also have the strain and all that in this medium. That's the other type of energy. So when we want to calculate the energy of this whole volume, well, we just integrate, right? We calculate the integral in this volume. Of course, that could also be an external field. So that's basically what we have to do. And so the whole energy of a quote particle, so of a soliton wave, is this energy in this volume of space. Now, again, I'm skipping steps because we have, the last video, 2021, has all the details, and otherwise my talk will be way too long. So basically what we're doing, we take this energy equation, we minimize with the Dubois-Raymond lemma, and Marek can answer any questions about this if you want to, and we get to the Schrödinger equation. So now there's not really much difference to the traditional complex Schrödinger equation. The only difference really is that we use quaternion. So it's not that much difference. It's not so surprising, really. So, and also if you look at the mechanical potential, right, the main difference is that, before we had, we just had one axis, really, the I, and now we have 3 axes of rotation, right? And you can actually do a projection if you wanted to. So you could always go back from the quaternion to the complex numbers if you wanted to. But at least to me, 3 axes of rotation make more sense than just one. So in summary, mass is really related to the overall dynamic energy in a certain volume. It's purely wave-based. So atoms, everything is waves. No matter there are no particles. It's all basically waves in this model. Gravity is caused by the space density curvature, like this sort of the graphic here, where you have denser areas, where, as Jarek was saying, when you have a denser medium, the wave speed changes, and that's basically refraction. And this applies not just to light waves, but also to matter waves, right? Yeah, and actually, I won't have time probably to talk about it, but just because last time I remember I got the question, special relativity is actually also part of this. It's an emergent property. Whenever you have a system of just waves, and by that I mean you measure with waves, because our measuring sticks are also composed of waves, right? Our clocks are made of waves. If you have an atomic clock, right? If you have this ultrafine, this sort of vibration, like these ultrafine energy levels, it's also composed of waves. If you measure everything with waves, it's very easy to show that you get special relativity out. And if anyone has a question, I can probably explain it at the end. So now what's the next step? Well, it's kind of obvious. Once we have Schrödinger, well, maybe we want to go to Dirac, right? That's kind of important because, matter, antimatter, and spin and all that. So So basically, that's what I want to do next. I want to now first just get into, just to first show you the belt trick, get into the Dirac equation a little bit, then try to explain how you can calculate this if you want to actually program it, in the computer, and show you how you can do visualizations. And of course, these are just examples, okay? There are other visualizations. So, and then of course, after we can speculate, well, what does it mean in terms of magnetism? Because, spin has to do with magnetism, right? So just to recap, and I'm sure most of you know this probably, what is spin 1/2? Like, what kind of properties does it have? Now we know that basically protons, neutrons, electrons, they all have spin 1/2, right? So I think it's kind of important to understand it. At least for me, I just want to know what it looks like. I just always wanted to know how it works. It is the source of the Pauli Exclusion Principle. Now the strange thing, right, is that it requires 720-degree rotation to return to the original state. Now, rotation is in quote because it's not really a rotation, it's an intrinsic angular momentum, and I thought a lot of people confuse that. So now the challenge is basically this. So you have a cup, right, and I actually attach strings to it, so you could try this in your coffee break if you to understand this. So you take a cup, and now you have to do this game. You have to spin this cup. So not like this, okay? You have to spin this cup continuously without spilling anything. You can't get up, and you can't remove your hands, and continuously you don't want to create any knots, okay? And your system, like your configuration, it has to be the same after 720 degrees. Now I'll challenge you to think about this and then actually really try this, okay? And it's called the wine dance, it's called the belt trick. There's many different names for it. It's not really so hard. So I have a recording in case I can't fit this into the camera here because it's kind of hard to do this all in one view. So you start to rotate, and there's actually two rotation axes. So one axis of rotation is this axis here. So that one's kind of obvious. You start to rotate, and now as you can see, I'm around once, and you can see it's not the same configuration. Yeah, I think you'll agree this is not the same. And now without spilling anything, you go up and then you're back, and see there's no knot. And you can do this continuously, and it takes a little bit of practice. It doesn't really fit into the camera here, I think, but once you understand this, and I did this probably like 1,000 times, so I could program it, you will see this is not really, it's not a rotation, right? You're not actually, so my hand is still attached, the strings are still, you can attach the strings in all directions. So the point here is, you could do this in an elastic solid. Imagine your living room has strings everywhere. You could do this in your living room with strings attached everywhere, and you will never get a knot. So this is a very kind of interesting kind of rotation. It's not really a rotation. So I think I'll skip the video because I think you probably saw that. So let's just briefly, just a few slides about the Dirac equation, and then I'll dive into the visualizations. So, well, as you know, right, Schrödinger equation has first and second order. Then the Clay-Gordon is second order throughout. So Dirac was looking for an alternative which was first order throughout and relativistic. So that was the challenge. So how did he do that? And what I read, it's like basically he just kind of wrote it down. There's this alpha and this beta. So what is it? We can do one thing we can do is we can write out the momentum vector here. We can basically write this out with alpha x, dx, and so on. Okay, now what? Now, of course, I'm skipping a few steps here, but because I won't have 2 hours. But if you want to, there's a really, really nice PDF that explains everything in detail in case you don't know. Oh, I skipped the slides, sorry. Now, of course, it has to satisfy the Planck-Gordon equation as well, right? So there are certain conditions these alpha and beta have to fulfill. So basically you have these equations that have to be fulfilled as well. Now, the thing is, when you look at this and you try to solve it, you kind of realize pretty soon, I think, there's no number that works. It doesn't work. So you have to use matrices which are anti-commuting, which makes it a little more complicated, right? It's like how does that work? So once you do that, I'm not going to do the steps again. You can read this offline. You come up with, the Pauli spin matrices. So basically, you have this beta, which is basically composed to the identity matrix. You have the three Pauli matrices, which is then basically part of this alpha, X, Y, and Z. And when you do the calculation, so when you actually multiply, sigma X times sigma Y, then you get I times sigma Z, right? So that's what you get. And I'm wondering, when you look at this, doesn't that look kind of familiar? I mean, I'm not going to say it right now, but it looks very familiar. I mean, when you see this, to me, it's kind of obvious, right? I'll say it in a minute if you don't see it. So what do we do with this? So basically, when you have a 3D vector, a normal 3D vector, and you multiply it with the Pauli matrices, you get something called a Pauli vector. It's just math. You just basically you take the X, Y, and Z, you plug it in, those sigma, you plug it in, and that's what you get out. That's not very complicated. The interesting part is that this Pauli vector, when you can factor this out into a column vector and a row vector. And these are now the Pauli spinors. So now it gets interesting. Now we're getting towards the spinor. Now there are two kinds of spinors. There's the Pauli spinors for 3D space and the Weyl spinors. Now I'm just gonna do the Pauli spinors. I don't want to have to deal with this. It's a bit complicated. So as you know, of course, it can be shown that the Dirac spinors represent the spin 1/2 particles. The really important part here is that the spin is intrinsic angular momentum. It's not orbital angle. It's a different thing. It's intrinsic. So it's not like the electron is turning around. It's the intrinsic thing. That's really fascinating. Just like I showed you with the cup. It's not that the electron is actually turning around. That's not what it's doing. It's the intrinsic movement. So only a few more like this, and then I'll have videos, a lot of them. Okay, so when in quantum spin, right, people usually use the quantum spin vector. So they would say, there's the alpha and beta. This is basically spin up. So spin up would be 1 and 0, right? And spin down would be basically the 0 on top and the 1 on the bottom. Now, because this is about probabilities, the square that has to add up to 1. And these values are complex numbers. Okay, so now we have to I'm trying to make the connection to the quaternion, so I'll get there in a minute. So what happens when we do rotation? So when we rotate a vector, a regular vector, right? We use a rotation matrix like R, for instance. So, well, how do we rotate a spin vector, right? Now, we call it U, and there are certain conditions that have to be met. Like, for instance, if you rotate a vector, the length has to be the same, obviously, and the same is true for the vector. So there are certain conditions that have to be met, right? So basically, these conditions turn this U into a SU2. That's a special unitary matrix with 2 dimensions. It just means that basically, as I was saying, the length has to stay the same when you rotate it. Now, let's say we didn't know what U was at all. Let's just call it A, B, C, and D. We don't know, right? No idea. So when we do that, well, we then now have to apply these conditions. Then we very quickly come to a conclusion, and there's a few steps, but it's not difficult. That this is what U has to look like. So you have only A and B now. Now remember, A and B are both complex numbers. So let's write these as complex numbers. So let's say A is a complex number with X plus IY, and B is also a different complex number, Z plus IW. Now, when we just simply apply this, then we basically plug in the complex numbers. You get X squared plus Y squared plus Z squared plus W squared is equal 1. Well, what does that look like? That's pretty obvious, right? That's the three-sphere equation. And now we're back to quaternions. So that's nice. So it means basically SU2 is equal to S3 as a topological space. And SU2 is isomorphic to the quaternions. And I won't have time to talk about the details, but basically we have shown that SU2 is isomorphic to quaternions. So now let's get back to these Pauli matrices. If you remember, we had these Pauli matrices. So now maybe you can see the connection that basically these correspond, the sigma x, sigma y, and sigma z, they correspond to the quaternion, the I, the j, and the k. And now we are back to quaternions. So now when we look at the rotation, it's actually quite simple. So when you rotate a 3D vector, right, that's what the rotation matrix looks like. When you rotate a Pauli vector, you get a half rotation, and then you get the Pauli vector in the middle, and then you get another half rotation. And we know now these are just quaternions. So because that's SU2 here, and this one also, this side is SU2. So we can rewrite this as this. It's just quaternions, right? So I think it's enough math for now. So let's look at some visualizations. Here is again, this is the belt trick. It just, instead of a coffee cup, I wrote a little program that shows basically the belt trick. And I'll explain in more detail right now after how to calculate this. So basically, this is angular momentum without rotation. It's the intrinsic angular momentum. And so just to point out the sphere here is only a visual aid. There's no sphere. I only added it so it's easier. You kind of, because you can track the rotation. That's why I added it. There's no sphere, and there's no knots or anything. So the ends here, they are attached and they're firm. They're not rotating or anything. So there's never any knot. So how can we calculate this? And actually, I got inspired a lot by Dr. Mark Snowswell, and I talked to him, I think yesterday, and maybe he will give a talk next time. He's really, really great. He knows all about spin. He knows everything about spin. He had this really nice idea of how, to simplify the spin calculations, basically. And basically the idea is that, when we calculate a spin function, there's really two parts. So one part is a function of time. This is the first quaternion here. So this quaternion function is a function of time. So that means the angles in here, the angles are a function of time, obviously, because we have these phases, right? And after it repeats after some amount of time. But if you prefer rotation matrices, you can always, transform a quaternion to a rotation matrix if you prefer that. But I think quaternions are easier. So this is the quaternion. This is the corresponding rotation matrix. This is one aspect of the spin. Remember, that's basically what I was showing here. This is this part. So the vertical axis, that's the function of time, right? Because I'm changing it over time. There's also another part that's the function of space. So let me just play this. You can call it the winding up of space. It's kind of hard to show with this one because basically my arm, that's like the winding up. My arm is not straight, right? There's this. I have to change. My arm has this winding. This is basically what it is. And he called it cat just because bracket. It's kind of funny. It makes it simpler, and he uses the symbol, so the opening for bra and the closing one for cat. And the S in the middle, that's sort of the kernel function. That's the winding of space. So again, you can normally, this is what we function of distance, and this could be 1 over r, could be 1 over plus or 1 plus r or something like that. Here's just simplified. I didn't want to show a long formula, so I just showed a very simple cosine. Yes, and then so now when you combine them, that's the function now. So now we have, so the spinor function is now, you have a quaternion, a function of time times the kernel, which is a function of space, and times, of course, the conjugate. Then you get this. Then you get the belt trick. That's basically the belt trick. Here is the summary. So basically, we have two functions, one function of time, obviously QT, and this is the identity matrix. And then when you combine them, you get the belt trick. And how to program is really, I can show you in the next slide probably. How you program this is basically if you look at this here, right? So at the end, at the very far end, in infinity, there's no winding, but it gets more as you go to the center. So you can imagine this as concentric shells if you want to program this, basically. So here, actually, let's see, how much time do I have? I can probably show this. Let me try if it works. So it takes a lot of memory to run this live, but let me try. So this is a Unity game development engine. And if you want to program this, so here I have the first bell trick, and now we can do a lot of things. So let me just change the winding to a very small amount. And now we have the phase. So this is one of the, this is the function of time here that I'm moving. So I'm just moving back and forth here. And the other one is the winding. So I can, if I have no winding, there's, it's flat basically. And I increase the winding here to 180 degrees. Then this is the point where we get the Dirac bell trick. So when I now move this, you can see, and it's nice because it's nice to have software, because then you can play with it. I can zoom in with the camera in and out and so on. So of course, the bell trick is not really what an electron would look like. Obviously, this is just for fun. So how can we make it look more realistic? Let me just move ahead a little bit here. Now bell trick is just one visualization. So now we want to do this in the Planck-Kleinert crystal, right? We want to do this in the elastic solid, because if this is if our universe is an elastic solid, we have to explain how spin works. That's what's basically the goal. So here I have indicated the elastic solid by just two planes. So there's just, otherwise, if I show everything, it will be messy. So just two planes. And the sphere, again, is only for illustration. There is no sphere, okay? And again, this is the winding that you can see now. And the arrow shows basically the direction of spin. So here, spin direction is actually down. So we can do the winding, and then play with this. And then when we do the spin, when you let it run, let's see, I think I'm letting it run somewhere. You can get a feeling how that looks like, that spin wave. Of course, again, there are actually there are infinite number of solutions. Okay, this is just the easiest one. There are very many solutions to this. You can have spinner within spinors and all that stuff. You can also have a torsion. You have a torus-shaped solution as well, and maybe I'll do that next. This is not, yeah. This is just one way how to implement this. So you could also, in this case, I added all the grid points so you can see what would it look like from far away. And from far away, it's just this wobbling motion. It doesn't really look like much. It's really just like a pudding that have this wobbling motion, right? That's basically what it would look like in an elastic solid. And again, this is pure waves. And I wanted to point out that many people are now working in this wave-based model, including all these people here. Manfred Faber to some extent, so he will also talk, I think. He has a very similar simulation for spin. And I just want to mention again that actually there's no sphere, okay? This is just for illustration. So this is more what it will look like if you remove the sphere. It's just a wave. It's just a transverse wave in this case. Now, I wanted to mention something else. So in this case, what I did, I added a lot of grid points here, like Smarties in a pudding, so we could see what does it look like? What is the displacement, at each point? Like what happens in this elastic solid exactly? What does it look like? And you can see there are little circles. So each point, and it's actually double cover. If you look closely, it's actually going around twice until it gets back. So it's a double cover. And in the program, I can zoom around, so you can actually see and try to imagine what it looks like from all directions. So each point in the elastic solid makes just a little tiny circles. And it's not always circles, obviously. It could be any function. This is just the easiest one, basically. Now, what I did next, I thought, well, what if we just use the thumb rule, and indicate direction? of the rotations, right? So when we do that, we get these arrows, right? And now you start to see you're starting to see what this means in terms of electric magnetic field, basically. So the spin in this case would be down. And next what I did, I added 2. Well, of course, we want to see what happens when you have 2. Let's say two electrons, for instance, right? So I know this is speculation right now, but I thought it looked pretty interesting. So here we have basically a spin in this direction. Both spins go in the same direction. And when you then calculate the displacement field for these 2 spinors at the same time, and you draw the arrows, it looks very much like attraction. And of course, it's kind of obvious when you think about this, because these movements, this spin movement, the spin wave, when it goes in the same direction, it's compatible. Like, of course, it would work. It would be basically resulting in attraction, because when you flip it around, so here I flip the right side around, and now it's kind of obvious it's no longer compatible, because you see on one side you have rotation going in one direction, and then the other side the rotation goes in the other direction. Of course, if you have an elastic solid, right, and you can't have one, in one side you go one direction and the other side you go the other direction, that will cause strain in there. And when you calculate this is what it looks like. So as I mentioned, this is not the only solution. There are many solutions. Another one is a torus-shaped function, and I didn't write this. I got this from the internet, but maybe I'll do this next. And also there are many oscillators. This is just the easiest one I did, but you can nest them in the solve. You can have spinors within spinors within spinors, as complicated as you like. And then so when you, for instance, make it just a little bit more complicated, it's no longer a circle, right? Then you get this more complicated, when you trace an element in the elastic solid, you get more interesting functions like that. So I know Manfred will also give a talk. I wanted to show, I hope it's okay, Manfred, I'm sharing what you showed me when we talked. So he also has, is that okay? Yeah. Okay, yeah. He has a very similar simulation, and we talked about it for many hours until we came to the conclusion it's essentially the same. And I thought that was nice. I think his program is in MATLAB. You get the same kind of belt trick. And again, thanks for Mark Snowswell. He's not here, I think, because he's in Australia. Hopefully he will be able to talk another time. So basically, well, that's basically it. And thank you very much for your attention. I do want to mention other people are working on this also, similar things. And I didn't list everyone, but Robert Close has done a lot of work in this area. He has many, many papers, not many pictures, unfortunately, but a lot of math. And I mentioned some others, Daniel Zhang, Donald Zhang, and many others are working on this. So hopefully, my wish is that more people will get interested in this topic to do more research, because there's so much more to do. Anyway, are there any questions?
Okay, welcome to the questions.
Actually, there are comments on the chat line.
Okay.
So there is James.
Yes, I'll have.
Hey, how are you?
I am good, and I'm going to have to watch this again. This is just fascinating stuff you're doing, Chantal. As you're doing the coffee cup, I realized when I was young, I tried to spin a baton without letting go of it. It's called a figure 8 motion.
Oh, okay.
And there's a little
exactly.
video here.
That
might be a good way to demonstrate this.
Yeah,
If you go in
that's a good idea.
This little video, later in the video, she shows really slowly how she's just sort of doing a figure 8, and the baton's moving around, but never leaves her hand.
Exactly.
So,
yeah, that sounds like it. Yeah.
Fascinating stuff, Chantal. I've got to watch more of this. This is just amazing.
I just having fun. So yeah. So Jarek asked something Brocket. Oh, the Brocket is this is just a shortcut. This is nothing, doesn't have any meaning. It's just, instead of writing quaternion this and quaternion that, it's just, it was just nice because in the software, I can just write a Brocket. I can just, use the symbols to create spin functions instead of having to type quaternion, blah blah blah. It's just a shortcut, so that's just a notational thing. It's just to be
It's more.
That's a big question. What exactly is this brown cat? So it's not such a simple question, and its side is the border rule, which is this whole Bell validation. So it's very very non-trivial question. What are brown cat?
Okay. Any other questions?
There are no relations from my side.
And also, any questions for Marek, because I didn't cover everything. So, again, if there's an opportunity to ask Marek any complicated questions, of his model. So.
May I give a small comment?
Sure.
Yes. I think what you show is that particles which have spin 1/2, they need 2π rotations in order to come to the original state back. So it means every body, every particle, for example, electrons, which are connected to the surrounding, they only return after 4π, after 720 degrees.
Yeah, exactly. Yeah.
That's what you show.
Yes.
But spin, of course, has two properties. One property is the quantum number. Spin has a quantum number. So you have addition of spin 1/2 plus spin 1/2 gives you either spin 1 or spin 0. And the second property of spin is that it contributes to angular momentum. And of course,
exactly.
You do something where you show that it contributes to, possibly to angular momentum.
Well, the total momentum is the angular plus intrinsic momentum, right? So basically, this is one part is the intrinsic, and then you still have the orbital. I didn't show the orbital one, right? I was just showing the spin itself. Of course, the electron also has orbital angular momentum, but it looks different.
But you can also add up two spins.
Yes, of course.
Electron plus 2 electrons in helium, for example.
Oh, of course. Yeah. Because,
to spin 1 or to spin 0.
Yes, of course.
So
yes,
this. But this needs a little more than you show us.
Yeah, you can help me program maybe.
There's also magnetic dipole moment associated with spin, also very important. And regarding 4π, so we don't need 4π. We only need that rotating by 2π, the objects becomes the same object. So if you say that this and this is the same, then you also get 1/2 spin. So
there's a difference. Yeah, there's a difference. So if I walk around the cup, of course, I only need one rotation. That's not the same. This is a different kind of. This is the intrinsic angular momentum. This is what requires 720 degrees. It's the intrinsic. So when you walk around, it's a different thing. That's not the kind. The same.
I'm saying that spin 1/2 is frequent in, for example, in liquid crystals. That you don't have to make 4π rotations, because after 2π you need that the objects becomes the same object, and this way you also get 1/2 topological charges.
So spin 1/2 definitely. Spin 1/2 you need 720 degrees. I'm not sure. I have not seen anything else like that.
No, you don't need. You just need that after rotating, by making full rotation of around, the field rotates to the same. And
yes, the whole configuration. The whole configuration is the same.
No, I think Chantal is correct. So if a body is connected with the surrounding, it returns only after 4π and not after 2π.
Yes, absolutely.
So
you can try it. You can't do it, but it's not possible. You get a whole mess. So.
A body which is not connected comes back after 2π, but the body which is connected by wires with the surrounding needs 4π.
You can ask ChatGPT.
You can get the topological defects with 1/2 spin, and we have discussed. So it's not that we just have to say that this object and this object is the same object. And for molecules in liquid crystals, this is standard. They use this 1/2 topological charge objects very frequently. So this is a simpler way. You don't need 4π rotations. Just 2π is sufficient to get spin 1/2. Okay, I will talk about it.
We will make it, but I don't think so. Let's Google it, because definitely not. It's not possible. You cannot do it. It's not possible. Anyway, any other questions?
I have another question, and this concerns your comment that as soon as you have waves, you have special relativity.
Yes.
This is of course true that the wave equation is relativistic invariant. But imagine you have a wave in a real body, in a solid, in a real solid.
Yeah.
Then it's not special relativity.
Moment, there's an
Because,
important
because then the Doppler effect is different in water or in air than for electromagnetic waves. The formulae are different.
Yes, so we have to stay in one medium. So of course, this is true if you're in one, let's say we live in a, I don't know, water world. Well, maybe it's a bad example, but you have to measure everything in the same wave system. So actually, I do have a slide if you want to, let me just show you real quick. Well, maybe. So basically, if you have, imagine a phonon ship made of phonons, okay, in a crystal. Now, let's say there's these aliens they're all phonons. Now they have measuring sticks, but these measuring sticks are also composed of phonons, and their clocks are composed of phonons too. So everything is the same system. Then when you have a stationary, let's have a very simple clock. Let's have a very simple clock where we have just, a phonon going up and down. That's one cycle. That's like one phonon second, okay? And the distance, we have a certain particular distance, right? It takes some time, like for us outsiders, right? It takes a certain amount of time. We can, in our clocks, different clocks, we can see how long it takes. Now, when you have a moving phonon ship, let's say, now when it's moving, now the path is longer because it's no longer going just up and down. It's making this path here, but the speed is always the same. A speed of a wave is always the same in a medium. Now, when the path is longer, it means it takes longer. So the moving clock is slower than a stationary clock. In a stationary clock, right, when you have two ships, one phonon ship is stationary, and it counts how many clicks it's doing. And then you have another one that's moving. This clock will tick more slowly because the wave has to make a longer path. So, but everything has to be measured in the same system. You can't have, water waves and you measure with wood. That's not going to work. You have to have the same. You would have to have a, water wave measuring stick and a water wave clock. Then you get special relativity. For any wave system, you automatically get special relativity and the Doppler and all that stuff.
May I ask you, if you have this water wave clock, is the velocity of the signal independent of the velocity of the ship? This is the question. This is the critical question. If the velocity of signal is the same for a ship at rest or a moving ship, then
so the wave. Right. So yes, for instance, water wave may be tricky because you have wind and all that stuff. But if you have like a phonon in a crystal, there's only one speed. There's, of course, assuming the density is the same. Of course, if the density changes different, let's say the density is the same or it's all homogeneous, right? Then there's only one speed, C, normally we call it C. There's only one, it's always the same, right? And so
this is
always the same, whether it's moving or not, the wave is absolute. It's in the absolute sense, in that phonon crystal, say, it's always C. Now, a moving phonon ship, right, will measure for the moving phonon ship, the time will move more slowly because all the paths are longer. Everything they're doing, if they're eating and measure whatever they're doing, all the paths are longer. So everything is slowed down. Everything they're doing. When the stationary paths are shorter, so that's why the clocks move more slowly when we move, because if we are composed of waves, and light is composed of waves, and we are in this elastic solid, then as we are atomic clocks, they are doing this thing, right? When we're moving, it has to go a longer path, so the cycles get slowed down because the wave speed is constant.
So you say the velocity is constant, independent of the
exactly.
of the emitter, of the velocity of the emitter.
Yes, exactly. And the thing is, that
because
when you measure it,
this does not happen for sound waves in air.
What do you mean?
Sound waves in air have different velocity depending on the velocity of the observer.
No.
Sure.
Well, that's because the observer in our case, a microphone, is a different matter.
But
It's not composed of
the
sound.
observer measures different velocities. Either it goes against the wave or in direction of the wave.
Wave
So it's
system,
C plus
right?
V or C minus V.
That's because your microphone is not composed of sound waves. You have to be in one wave system. You know what I mean?
Yeah.
If you do the sound example, you would need a microphone composed of sound waves, which is kind of hard to do, I guess.
Okay. So you say velocity, they measure all the same velocity.
If you're in that system. So if you are in a phonon universe where the people are phonons and the measurement, the microphones are phonons, everything is phonons, then yes, it would be.
Yeah.
And they get time dilation, space contract, all that stuff you get automatically.
Yeah. Thank you.
Sure.
Thank you. Do you have new questions?
I mean, there are some comments from the chat. James, you get another comment, I guess.
Oh, sure. The two batons, the first baton, it looked like was more of a 2 pi. The second one, a different person's demonstrating it, and she's doing sort of a 4 pi technique. So, interesting what the actual half spin is. But these seem to be interesting analogies because they're so easy to visualize, and you can do it with your own hand.
Oh, I'll take a look.
If you could
totally
take a look. Yeah, thank you.
I have one suggestion actually for Chantal. I mean, thanks for very inspiring talk. Is there a chance you can be more involved in there's a panel discussion session, and can you think about a kind of introduction for students explaining the details of software created by you, something like that? I mean, I have various computer science students interested in those things.
Oh, okay.
And I mean, but simply, I have a certain skill of making computer science guys to be more kind of physics-like, like Dirac Kotula. Dirac, could you show your face? Because he's recently defended his Master of Science thesis with distinction on classical and quantum conway game of life.
Oh,
and
cool.
Now, now he's on in his perception of the world, trying to grasp deeper and deeper physics concepts. But so do you have any insightful and intuitive course for computer students?
I don't have a course, but I could talk to him if you want to. You can send him my email and we'll just chat.
Yeah, but I mean, is there a chance you can make extra presentation about more kind of computer science aspects of approach to your simulations, something like that?
I'll think about it. I'll think about it if I get the time. It's always a question of time.
I'm sorry that I have so kind of high expectations, but somehow I see that this discussions that were triggered definitely show a certain interest of
yes.
audience.
That'd be nice. I would love to have, if people were interested in this, do more research. Yeah.
Yeah. So let us somehow probably kind of direct the continuation on. There is on 12 July, there is a day about ontology of quantum mechanics. And there is also one day, and after that day, there is another day with a panel discussions. So it would be great if you could, trigger more kind of description and points you already made, right?
Sure, I'll try.
Thanks.
Okay, next questions. Okay. Maybe I will ask, but I have a question connected with the previous presentation. You show the longitude velocity higher than speed of the light. It is the maximal speed which can be obtained in your model, or it is the only example? In the previous presentation of Professor,
I think I understand your question. I wanted to, a few seconds before, I wanted to make similar comments to Professor Faber. In fact, we are surprised. We have already equation of for electron, wave velocity is the velocity of light. In within the wave itself, within the electron. The same is for boson. Wave in the boson particles have the velocity of light. But then there are systems of equations and other particles where velocities are different. They vary between velocity of light and velocity of longitudinal wave. Velocity of light multiplied by square of 3. So they are different. What I remember, I think Dr. Smeltzer was working on. You see, they are definitely different velocity. Now, why? There is a very nice explanation for this why. Boson creates gravitational field. Yeah, that's obvious. Yeah, there is gravity, so this is certain energy is accumulated in gravity field generated by a boson. Of course, when boson collapse, annihilation, matter, antimatter, energy cannot disappear. Definitely cannot disappear. This is problem of collapse of the wave function. Yeah, this is the same problem. What happens? Frankly, I don't know, but I could expect that this will create a wave which is faster than light. Could such phenomena. Normal behavior of standard generation of gravitational wave means not annihilation but collisions. Collisions create waves with velocity of speed of such wave is velocity of light. But you know, this is a very difficult problem. We don't know answer. And this is just my free thinking. At certain phenomena, yes, velocity gravitational wave has gravitational transverse wave created by gravitational collisions. Then there's problem of definition, of course. But when in a certain condition, you cannot exclude creation of longitudinal wave. In every medium, in what we know in material science mechanics, there are different velocities, transverse and longitudinal. Definitely. Differences are very big. That's all.
Okay, thank you.